Welcome to AI for Good, the leading, action-oriented, global and inclusive United Nations platform on AI. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with 50+ UN sister organizations and co-convened with Switzerland. The goal of AI for Good is to unlock AI's potential to serve humanity. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Welcome all to today's session, GeoAI and Earth Engine, AlphaEarth Foundations on the Satellite Embedding dataset. My name is Rohini Swaminathan, working with the Climate and Environment Data Unit in UNICEF, and it's an absolute honor for me to introduce a new episode in GeoAI Discovery Series, and the first one for 2026. So Happy New Year, everyone. This series was launched in the beginning of 2022, so it has been consecutively running for 4 years, and we have been organizing over 40 episodes so far, a combination of webinars, hands-on workshops, and several GeoAI competitions as well. Current focus of the series is on geospatial large language models, and in the organization of quite hands-on workshop focused on building up practical skills in applying AI to geospatial data. And this is being done under the leadership of the curator of the series, Professor Maria Bravelli, and our co-moderator, Andrea Manara from ITU. If you missed some episodes in the past, don't worry, you can definitely watch the recordings of those events either on YouTube or on our neural network to which you're connected right now. Without further ado, let me now introduce Professor Maria Bravelli, who will moderate today's event. Welcome, Maria.
Hello. So good morning, good day, everyone.
Thank you for joining us. Maria is Professor of GIS at the Politecnico di Milano at Geoinformatics Engineering course of study, and also the member of Schools of Doctoral Studies in Data Science and Earth Observation at Roma La Sapienza. Amongst her many impressive activities, Maria is also the Vice President of the Commission of Geospatial Information of ISDRS, Vice President of the International Society of Digital Earth, as well as the member of the board of the UN Global Geospatial Information Management Academic Network. Maria, the floor is yours to introduce our speakers and the session today. Over to you.
Thank you, Rohini, and I'm very excited. This is the first episode of this year, 2026, and we start with something that is super interesting. So we are speaking about Google Satellite Embeddings, and we can say that this is a revolutionary image collection that leverages multi-source, multimodal deep learning to help everyone create better maps faster and with fewer manual annotation. So what we are doing to see now is, first of all, a brief overview about AlphaEarth Foundations, for those who don't know this new technology. And then we will see, we will explore the AlphaEarth Foundations embedding space. We will see how satellite embeddings can be used for pixel-based similarity search and for implementing, and we will see how it was implementing a based supervised classification workflow using the Earth Engine API. So now I'm very glad of introducing today's speakers, and I can say that I'm very happy because today this edition is completely managed by ladies, which is not so common in the case of AI, but it means that also this pink presence is emerging, so I'm very happy about that. So our first speaker is Valerie Pasquarella. She's a senior research scientist at Google, where she works on developing foundation geospatial datasets that make Earth observation imagery more useful and usable to all. Valerie has a background in ecological applications for remote sensing, with a specialization in time series analysis. She earned a PhD in geography, a master in environmental remote sensing and GIS, and a bachelor in environmental science from Boston University. And she served as postdoctoral fellow with the Northeast Climate Adaptation Science Center at the University of Massachusetts Amherst. Before joining Google in 2022, she held research faculty appointments at Boston University and Harvard University. So congratulations. And then I want to introduce also the second speaker, Kathleen Tario. She's an Earth Engine solution scientist at Google, focused on providing technical assistance, remote sensing expertise in country training to support national efforts to mitigate emission from tropical deforestation. Kathleen holds a Bachelor in Environmental Science and a Master in Environmental Remote Sensing and GIS from Boston University. She's where she's currently completing her PhD on satellite-based monitoring of commodity-driven deforestation. So congratulations also to you, and now I leave you the floor.
Thanks so much, Maria. And welcome everyone to our webinar on AlphaEarth Foundations and the Satellite Embedding dataset. I'm going to come over here and share our presentation. And hopefully everyone can see that now.
Yes, yes.
All right. So today, as I said, we're going to be talking about AlphaEarth Foundations and the Satellite Embedding dataset, or GeoAI in Earth Engine. Just to give a bit of background, I'm pretty sure I don't have to convince anyone here who's been working with Earth observation data, but we really are in a golden age, not just of Earth observation sensors, platforms, data availability, but data archives themselves. In the Earth Engine data catalog, we have over 4 million images from the Landsat 8 and 9 sensors. That's not even including the legacy 1 through 7 missions. We have 31 million Sentinel-2 L1C images, over 3 million Sentinel-1 images, and these archives continue to grow. For example, Sentinel-2 adds about 100,000 images per week. So this is a huge volume of Earth observation information. And it's not just, a few sensors. We also continue to see more sensors coming online, both the non-commercial or publicly available satellite data, as well as commercial operations, government satellites. So this data volume just continues to increase at a rapid pace. And you would think all of this measurement really should be a good thing. We have so much data. We're looking at our planet at a higher rate than ever before in the past. We have more types of measurements, but there remain significant barriers in terms of expertise and resource availability that make it really hard to get the most out of this multi-source, multimodal geospatial data. So just to give an example for those who are heavily involved in remote sensing processing, there are a lot of steps between having those images available to you and actually getting to the sorts of insights that you want to have about our planet. And this involves things like all the steps of SAR processing, noise removal, terrain correction, phase unwrapping, optical imagery. You have to do things like atmospheric correction, cloud and shadow masking, BRDF correction. And then all of those steps, then you have to take the combined results and do some sort of feature extraction. This might look like texture metrics or harmonic model fits, image composites if you want to combine things through time. And once you've gotten just to that point, we now at least have our inputs that we can go on and do further modeling and analysis that we then derive insights like how much forest is being lost in a given year, or how surface water is changing through time. And so this is a lot to learn. And again, it makes it very hard to leverage these diverse image sources and actually get the sort of planetary scale insights that we're looking for. And that's where AlphaEarth Foundations comes in. So AlphaEarth Foundations is designed to take advantage of these repeat observations. We've got lots of sensors imaging the same place and building up what is essentially a video series of our planet's surface. And we take all of these observations, these videos, we put them into a deep learning model, AlphaEarth Foundations, and generate a embedding or a representation that compresses all of that information into a vector feature representation that we can then use for downstream analysis and insight generation. And so today we're going to be starting with, as Maria mentioned, a brief introduction to AlphaEarth Foundations. What is the model? How does it work at a very high level, just to give you some groundwork there. We're then going to get into the satellite embedding data set. So if AlphaEarth Foundations generates embeddings, the satellite embedding data set is our collection of analysis-ready geospatial embeddings produced by AlphaEarth Foundations. You don't have to run the model yourself. We've already run it to produce this image collection for you. We'll then get into a bit on similarity search. So this is something that's very common in embedding analysis in general. So embeddings are not unique to Earth observation. They've been around in ML for a very long time. They're used for language, for images, like camera images. And so we're going to use our satellite embeddings and apply this similarity search technique to start looking at patterns in both space and time. We're going to then get into supervised classification, kind of the 101 of combining embeddings with labeled data, and help you start to see how you can generate more accurate maps using very low numbers of observations, relatively speaking. And then we'll end with some examples of real-world applications, how we've seen folks using AlphaEarth Foundations in the satellite embedding dataset, and end with some Q&A time. So let's get started. I think the most important thing for those who want to follow along, I've got the link up there to this presentation. So goo.gle, GeoAI in EE ITU 2026. That should take you to the slide deck that I am showing, where we will have all of the links to hands-on materials, additional resources, and this deck will stay available to you after the presentation so that you can go back to all of these materials. So I am noting the little Earth Engine gear there. Those will be in sections where we've got a hands-on component. If you are following along, there's no setup required, no accounts for our demo app. So we've got a couple of apps we'll be using today. Those are available to everyone just as web URLs. For the Earth Engine components, if you want to run the scripts, those do require an Earth Engine account. Don't worry, if you haven't got an account yet, you can still sign up at earthengine.google.com. The account may not be available to you today, but you can always just follow along, save those script links, and revisit them later. So also worth noting, Earth Engine is free for non-commercial use. So all of you researchers, NGOs, non-commercial organizations, you can get this account totally free of charge and work on all the code and play around with our examples. And again, we'll leave time for Q&A at the end. So diving right in, AlphaEarth Foundations. As I mentioned, we think of this as a virtual satellite that we're building on top of EO data streams or videos. For those who've encountered ML concepts before, this is a super simplified overview just to give you a sense of what's going on, but you can think of AlphaEarth Foundations as a basic encoder-decoder type model. So we've got data streams coming in. In this case, we use Sentinel-2, Landsat 8 and 9, and Sentinel-1. They go through a video encoder that generates a latent representation. In our case, this is a 64-dimensional space. And then we use that representation in combination with specific time bounds to then decode into different targets. And so what we're able to learn is the relationship between those input sensors and our targets, with a bunch of other constraints that help build structure the embedding space that I'll talk about a bit more in a few slides. But if that's the super high level overview, let's actually go in a little bit deeper and talk a bit more about the specific components of the model. So I mentioned we start with an encoder block. I said that was my simple view. This is the figure from our paper. The link down at the bottom there will get you the full archive, and you can definitely read more about the methods there. Encourage you to scroll past the references into the supplemental materials, as there's a lot more detail in those supplemental sections. But really, we've got, again, our raw data sources coming in. These are video series, so we've got time-stamped images from our different input sensors. They flow through a set of pre-processing blocks, one for each of the sensors, and are then concatenated into this big, chunky feature vector. So that green block kind of in the middle of the box here. That feature vector then flows through our space-time precision, or STP blocks. And this is really the meat of the model. This is where most of the parameters live. This is where most of the learning happens. And space-time precision is a custom architecture we designed specifically for geospatial Earth observation data. And these blocks are incentivizing learning across three key axes here. We've got our space, which is accounting for spatial dependencies at kind of image or patch scale. So this is longer range relationships. Each of our images, I should say, going into training is about 1.28 kilometers on a side. So our space block takes care of looking at that 1.28 kilometer resolution and learning things kind of at that zoomed out scale. We then have a time component. And so this is where we take advantage of that video series, and we're using our time axial attention to capture temporal trajectories. So how in that video series do we see the surface evolving through time and actually being able to capture things like phenology, other seasonal changes, really the evolution in the temporal domain. And then finally, so we have a space block, but we also deal with precision. And so it's not just about longer range spatial dependencies. We have precision in there to help us capture very localized details. Think small, this is a 3x3 convolution, so the very localized relationship. And the combination of the space, the time, and the precision, we then share information across all of those pieces using Laplacian pyramid exchange, which means that the end embedding is not representing just space, just time, just local, just kind of more global or patch level relationships, but really the interconnection of all of them. And so we then, if we've got our, things coming out of our STP blocks, that is our out features in this diagram, we then repair with the time codes and get to the second most important part of the model that I would like folks to walk away maybe having a base level understanding of, which is our temporal summarization capability. So we've now got features that are capturing all of those spatial and temporal relationships, but we want to not have a giant stack of features from all of these different images. What we really want is that single compressed embedding, and that's what temporal summarization does. Essentially, the model is given a start time and an end time we call a valid period, and the model is asked to generate an embedding, a 64D compressed vector for that summary period. And so this is, you can almost think of it like compositing. This is how we go from the big tall vector with all of the timestamps down to something that does actually summarize a specific time period for a specific location. And that little colorful square, that is the actual embedding. Here we've got for each XY location, so each latitude, longitude at a 10-meter resolution over a specified time period, we get that 64-dimensional embedding vector. And that's kind of the inside wondering how we actually learn anything. That's where our tasks, particularly reconstruction, comes in. So once we have that embedding, how does it get to be good at the things we want it to be good at? How does it learn across different sensors other than our input sources? And this is where we reconstruct different targets. So we take that embedding, we are going to sample from a distribution for around that embedding, and we're going to use those samples to then reconstruct what we call target sensors. And I'll get more into what those are in a second, but this is asking that embedding space to be able to reconstruct something that it hasn't seen before. This might be a Sentinel-1, Sentinel-2, or Landsat image that was not included in the input set, or images from other sensors. And really, this is how the learning happens. So it's information flowing in, getting compressed, but then the model only wins the prize if it's able to then take that compressed information and translate it back into accurate, meaningful pictures that we can compare to real observations. And for all of the EO scientists in the room, I'm sure you're wondering, well, what data sources are actually going into this other than those input sensors? We have a whole list of multi-source Earth observation sources. And so other than the optical, thermal, and C-band SAR that we're getting from Landsat, Sentinel-1, Sentinel-2, we also include L-band SAR as a reconstruction target coming from ALOS PALSAR, ScanSAR data. We've got the Copernicus DEM to give us elevation information. We've got JEDI LiDAR returns, specifically all of the relative height metrics. So we've got that full canopy profile that we get from JEDI. Climate data from the ERA5 land data set, including precipitation, air temperature, dew point, and surface pressure. We use gravity fields from GRACE to tell us about liquid water thickness, specifically getting at more groundwater there. And we've got a bit of a very weak supervision. So we pull in land cover information from the National Land Cover data set, as well as there's a note at the bottom, we added in our latest iteration some crop type information from the USDA NAS cropland data layers. And on top of all of that, we also have a pathway where we include geocoded or geo-registered text information from Wikipedia and GBIF. And all of this gives us a massive amount of information to learn from. In total, our training data set for the AlphaEarth Foundations model includes over 5 million individual sites distributed globally. For each of those sites, we pull video series for 2 different time periods. So that's a total of 10 million video clips. And at kind of grand total scale, we have over 3 billion images being fed into our model. So it's very well-trained model and globally representative with lots of different data sources going in. And one of the last things I'd like to talk about in terms of the model itself, we talked a bit about reconstruction, but it's really not just the reconstruction objective. So while reconstruction is where we're able to reconstruct those randomly selected frames or other data sources, we need the metadata and time codes for that. That's part of the structuring of our learning algorithm. We don't actually tell the model anything about X, Y, or sensor angles or anything like that until we're about to reconstruct. So the embedding doesn't know specifics of location, but we use that information, or we use the metadata information around, like, again, viewing geometries, those sorts of things, to then help with reconstruction. On top of reconstruction, we also have what we call our batch uniformity objective. And this is another constraint in addition to that reconstruction loss that helps encourage our embeddings to be uniformly distributed on a 64-dimensional unit hypersphere. Now, it makes my brain hurt to try and think about a sphere in 64 dimensions. So if you just want to picture a regular 3D sphere, that's probably the easiest way to do it. But really, this is the idea that the embeddings are well distributed across just the surface of this space. So we constrain the way the embeddings are learned so that they're actually on the surface, not kind of in the sphere volume. And we pick random batch elements, and we make sure that there is a that they're well spread out, best way to say it, on the sphere, giving us both a standard range and making sure that everything doesn't kind of bunch up in one portion of this feature space, which is great when you're trying to do things like tree-based classifiers or clustering. Next, we have our contrastive consistency objective. So if batch uniformity is helping us make sure things are well distributed, contrastive consistency is making sure that we can deal with the inevitability of remote sensing data where we have to deal with missing inputs. So for example, with the Sentinel-1B failure, making sure that when a sensor drops out, we're not affecting the embedding result. And so here, we are dropping pieces of our video series in order to keep those embeddings robust to the missing inputs. And finally, one of the things we get asked about the most, our text contrastive objective. So this final piece of the puzzle is where we actually ask the embeddings that are being learned from our Earth observation portion of our model to align with embeddings that are coming out of text descriptions. So imagine for each of the Wikipedia or the species associated with a GBIF observation, for those we pull the associated Wikipedia article, we get a text embedding out of that, and then we ask the Earth observation embedding to essentially align with, to be able to go between and predict from that Earth observation embedding the text embedding. And this embeds an additional amount of just semantic information. So imagine species descriptions include lots of things about habitat, distributions, that sort of thing. Wikipedia is describing the physical features of the Earth's surface. And so this, again, incentivizes the embedding not just to distribute in random space, but to have some semantic meaning to assist with downstream tasks. And that was a lot very quickly, but if all you take away from this section of the presentation is this idea that AlphaEarth Foundations is a virtual satellite. We take these non-uniformly sampled diverse data sources and we effectively turn them into a single continuous record that we can synthesize over a given time period. Again, think like a composite. We can pick a single date, a week, a month, or a year, and generate an embedding that represents that period from this continuous record. And that synthesis is what we call a embedding or embedding field, because these are continuous coverage for the Earth's terrestrial land surface, so designed to be spatially explicit. And with that embedding field, again, we have a 64-dimensional vector for each 10-meter pixel in the field. And if you were to sample any one of those pixels, you would get the associated embedding vector, which is situated. Here's our visual of that 64-dimensional hypersphere in 3D for simplicity. So that's kind of the core of what our embeddings, how dimensionality, resolution, and what the embedding vectors are, which segues us nicely into our satellite embedding dataset. So the satellite embedding dataset is our collection of analysis-ready geospatial embeddings. And these are annual summaries generated by AlphaEarth Foundations. Remember, I said we can generate for any given time period, but we specifically started with calendar-aligned annual embeddings as an image collection, just because that's kind of the best starting point. And a lot of folks use annual time steps for things like land cover mapping and all sorts of other applications. And so this data set is available in the Earth Engine data catalog. It is CC BY, and again, Earth Engine is free for non-commercial use. So this is just readily available, already processed. We've run the model and we've got those embedding annual layers for the years 2017 through 2024. And we're in the process of generating the 2025 layers as we speak. So with these annual summaries, let's get into our first hands-on portion. So we just to start and get to see some of what's in the embeddings, we can go in and we've got this very cool app. I'm going to share it in live view here. And what this effectively does, these are the 2024 embeddings. We are visualizing just 3 dimensions of that embedding space as an RGB image. So think, when you have an optical image and you plug in the red, green, and blue channels to get a color composite, we're effectively picking any 3 of those 64 axes of the embedding space and visualizing them as an image. And here we've got the first 3 axes, but I've got this fun button called randomize, where it will randomly pick the different axes that are going into the composite. If we give it a second to load, we'll start to see the colors are changing. And really what you can see here is the sorts of information that is being captured. We can see patterns like in this combination, which I just randomly picked now, so no pre-baked here. We can see some of the cities and fields are showing up in this very green color, so it seems to be pretty strong in A25. And the tool also allows you to go in and look at the individual axes in grayscale if it's harder to think in the color composite. So I guess we could say here, A25, the city is relatively dark, where it's a little bit brighter, and we're getting those finer linear details in A6, but really an exploratory tool, not something you're going to use for any sort of scientific analysis, but this is just an initial look at how much information is in these embedding space and the fact that it captures these very real spatial patterns. So let me zoom out before we get back into the presentation mode, and why don't we let this load for a second, and we'll get to see some of the global distribution of these features here. And you'll see, I'd say, like things like, again, linear features, sometimes those like larger scale climate patterns that have been learned will show up. Those will be a little less crisp when you look at the grayscale, a little bit blobbier. We can see different land features, different water features, really showing up in these different colors, which again indicates that the embeddings capture distinct properties, whether those be spatial configurations, spectral and measurement space, or the temporal trajectories, which are encoded there as well. And as I mentioned earlier, this app anyone can access, so I would encourage anyone who's interested to keep playing around, look at your different color combinations. It's hard to ascribe any particular meaning to these axes, given that they combine so much different information and so many different planes, but it does really, again, show you kind of the richness of the information content in the embeddings. So hopping back over to the presentation, let's actually start working with the embedding. So that's an app. We're just getting kind of a view into the data set, but I'm sure folks who are doing their own analysis want to know, how do I actually work with this data set? Well, again, the data set is available in Earth Engine. Embedding fields do have this continuous spatial coverage, but in order to serve them, we serve them much like a Sentinel-2 or Sentinel-1, a regular image collection, where we have chunked the world into these larger tiles just to make it easier to filter, to query, otherwise kind of break down the entire globe into smaller chunks. They do connect at the edges, so you still get those continuous coverage, but we have these individual tiles, and within those, again, the embeddings are a 10-meter resolution, and we have the embeddings for the years 2017 through 2024. So let me very quickly show you, and for those who are following along at home, feel free to type along with me in your Earth Engine account. But if you were coming fresh to Earth Engine, you would see the code editor, which looks like this. So we've got a search bar up here at the top, and to find the embedding data set, I'm just going to type in embeddings, and hopefully this will return the satellite embedding collection. And if I click on that link there, I can easily view that same description I saw on the data catalog page. And if I want to get started, I can simply click import in our GUI here, close out this dialog, and there we go. There's the satellite embedding image collection in Earth Engine ready to use. But you may be wondering, okay, well, how come I can't see it? Well, in order to look at the image collection, we're going to have to do a little bit of coding. And before we even get to the fun stuff on the map, why don't we just take a second and prove to ourselves that I was telling the truth when I said there are 64 bands or axes to this collection, a little bit more about the tiles, and we will print the very first image in the collection. So here I have now printed the first image, just whatever's first in the entire collection, to the console here, which allows me to view some information about that image object. You can see if this is a large collection of images. Here we're looking at a single image. You can see that that this image has those 64 bands. We've named them A00 through A63 to indicate A for axes. They really aren't bands. They don't correspond to physical measurements. They are these axes of a learned embedding space. And we can see the variable name there. And the images have a number of properties as well. You can learn about the data set version, model version, which UTM zone this data set is in, as well as the time range over which the image is from. In this case, it should correspond to the start and end of a given year. So pretty basic properties, pretty obscure names. If you actually look at, I believe this is the ID here, the tile numbers are sort of non-human readable, but almost intentionally because they really are just these chunks of the Earth's surface. But that is kind of the printed version of the image collection. What we really want to see, I'm sure, though, is what this looks like on a map. So let's go ahead and add the image collection to our map panel down at the bottom. And I'm going to let this come up slowly. Bigger tiles take a little longer to load, but there we go. You may be thinking, wow, this is kind of dark. I wonder, I just showed this very colorful example in the app. This does not look very much like that. In fact, I see a lot of kind of those standard RGB colors. Something seems off. And you'd be correct for a couple of reasons. So I mentioned earlier, the image collection actually includes all of the years of embeddings. So by just adding the layer like this, we're taking the full set of the embedding images and sort of mashing them into an average. And if I zoom in and click on the map with our inspector tool in Earth Engine here, you'll see it says layer 1, which is what's added to the map here, is a mosaic. And if I scroll down, you'll get a little bit more info. Actually, this is 8 different images corresponding to our different years here in the embedding series. And so those are all being combined and displayed because we didn't tell Earth Engine that we wanted to look at anything particular. We've got, the entire global collection and we've got it for all years. Not really what we want here. So let's start to filter this down a bit. I'm going to do this by, in the simplest way, I'm going to use Earth Engine's drawing tools. And I'm going to add a marker to the map. I'm just picking a random location for illustration, but feel free to zoom to anywhere you like. In fact, you can use the search bar up here, not just to look for data sets, but you can look for places based in New York. So you could say New York, New York. And in fact, you know what? I'm going to delete my point here and move over to New York just so we have a little local flavor. And let me drop a point. There we go. And so now I have this new object called geometry, and that corresponds to my dropped point. And I can now use that to, let's create a new variable called embeddings filtered. And I'm going to take the image collection, that embedding collection, and I'm going to filter bounds, which is a function in Earth Engine we use to filter based on spatial locations. And I'm going to filter to just that geometry. I'm going to then, let me get my spacing correct, add another constraint where I want to say I don't just want to pick only the tiles that intersect my New York location here, but I also just want the 2024 embeddings. And I'm going to do that by saying filter date. I can pick the start of the year, and then I'm going to say 2025-0101. Earth Engine end dates are actually exclusive, so this will give me through the end of the day before. And that's going to give me a filtering of that full global collection down to just the tile that I'm interested in. However, you can see if I run this code, still just getting my printed image from the command up here, and I've filtered the collection, but nothing's happening. It's because I haven't actually told Earth Engine to add it to the map. So now let's go map add layer, and let's say embeddings filtered. And let's just go ahead and add that to the map. And I'm going to turn off that original layer. And what you can see is we've now pulled a single tile. But it still looks kind of dark, huh? Not like, again, what I showed in the app where we had these beautiful colored images. That's because we're missing one last step here. And what we can do in order to actually see our embeddings, we can pick a specific set of axes that we want to look at. So let's go ahead and say for our styling here that we actually want to look at, let's mimic the way the app starts us off and say bands A2, A1, and A0. Let's also then set a min. The embeddings are scaled, already normalized. They're unit length vectors, which means each vector has a length of 1, and those go in the sphere, so they go in a range of -1 to +1. Usually we find that a min of about -0.3 and a max of 0.3 gives us some very nice scaling. And let's actually name this embeddings when we add it to the map. I'm going to comment out that original image collection ad so it's a little cleaner to look at. And voila, we have a single embedding tile for our region of interest. We are picking which bands we want to display, and we're scaling those bands so that those colors really pop in the map. Now, you can imagine if you go back to that RGB app, you find a color combination that you like to use that you want to visualize over here in the code editor. I'm just going to pick some random numbers, but let's say, all right, let's try axis 45, 6, and 10. Let's see what happens here. There you go. So we can change our styling on the embeddings to just view them in whichever slice you want. You're not seeing the full 64-dimensional space, just those 3 channels at a time, 3 axes at a time. But this demo is really showing you that structure of the image collection, how important it is if you want to pull out particularly the time component to be able to filter by year. And again, if you don't want to be working with the whole world all at once, being able to filter by those tiles. But those tiles do abut to each other, so also easy to go back and scale things in order to actually make use of the full global coverage. So I'm going to go back over to our presentation. If a little too fast, weren't able to follow along as I was typing, there is a link to a script here that will give you the same demo example with all the steps worked out if you want to revisit this later. So that's all available to you. And again, these are kind of the most basic steps we use when we are loading the embedding data set. That somewhat concludes our initial intro tour to the structure of the data set, how to visualize it. I do want to mention, for those of you who aren't Earth Engine users, that we hear often, I work in Python, I work in the larger cloud ecosystem. Is the data available outside of Earth Engine? I am so pleased to be able to announce that in early December, we launched a copy of the Satellite Embedding dataset on Google Cloud Storage. We have a Medium article linked there, tells you more about how to get there, how to work with it. These are the raw unquantized embeddings. So we actually store our embeddings as bytes in order to reduce storage cost. When you see them in Earth Engine, they've already been rescaled back to floats for you to make it a lot easier to work with without additional code and processing. But the Medium article will explain the differences between the Earth Engine collection and the cloud storage collection, and those who want to go and either download embeddings or integrate them into other parts of cloud. You want to use them with Vertex or BigQuery. Here's a copy that you can use for that. Data set logistics covered. You must be wondering, and I alluded to this earlier, but what can you actually do? So it's fun to look at these pretty rainbow maps, but what we really want to do with embeddings is put them to work just the way we do satellite imagery. And we can do all of the standard remote sensing applications, think classification, so categorical variables, regression, those continuous biophysical measurements, field records, and change detection. So embeddings are temporally consistent. I mentioned our consistency through time and our different objectives. One of those is designed to make sure that each year of embedding should be comparable to the year before. So if nothing's really changed in terms of the measurement space, which again includes both surface properties, climate, other variables, the change should be, you should be able to look for change in embedding space and have it be meaningful and that the embeddings are consistent. But Similarity search is one that I feel like a lot of EO scientists may be a little less familiar with, because this is something that's very specific to embedding vectors and feature vectors. So that's actually where we are going to start. So in our deeper dive into working with the embeddings, we are going to start with similarity search. And for this, we are going to use a fairly simple method or dot product similarity. Going back to some long ago math courses, if you've been out of school for a while, or maybe this is really fresh for those who are still in their programs. But dot product similarity is how we compare two different vectors. And I've got a little illustration here to kind of break it down visually, but you can imagine that we've got that 64-dimensional sphere. We're going to picture it in 3D so our brains don't hurt. We've got a first vector. We are then going to use the dot product similarity to look for the angle between vector A, the blue vector, and vector B, the green vector. And as those vectors can spread further apart, the dot product similarity is going to give us the cosine between those vectors. So as they get about perpendicular, cosine is going to be about 0. And as they get to completely opposite, the cosine will be -1. And so what we do to get the dot product, it's very basic. More or less, we take the first vector, we multiply it by the second vector, and then we sum over the products. So I've said before, I feel like this is sort of like the NDVI of embeddings. It's very simple math, but it's super powerful because unlike those RGB composites where we're actually looking at just 3 channels at a time, we are actually comparing the entire vectors, those full 64 dimensions of information in the feature space, and looking for deflections between 2 vectors, either from different locations, or we'll see in a little bit from different time periods. So that's the basics of dot product similarity. What we're going to get out of this calculation, again, is a cosine value on the scale of -1 to 1. You may also hear this referred to as cosine similarity. Our embeddings have the nice property of being unit length, so we don't have to normalize the magnitude. The full dot product calculation will take into account you could have to normalize your vectors first. But here we've got our dot product. And before I go into more on how we do this, let's look at some examples of why the dot product is as powerful, is such a powerful tool. And here in that little white square, I've actually got a box around some mangroves on the fringe edge of a delta in the Mekong River in Vietnam. The location's up in the corner if you're curious, but let's look at those mangroves and let's pick a point and see, in terms of dot product similarity, how similar is a selected embedding vector to every other embedding vector in this viewport? And if we calculate the dot product in Earth Engine, I've got some tools for you to do this yourself in just a sec, but if we look at that little black dot is where I've picked an embedding vector, and in this map view, each pixel is being scaled. Darker pixels have a more divergent dot product, so they are less similar in embedding space. The brighter a pixel is, the more similar it is to our selected location. And you can see here that not just what's along that very fringe mangrove, but lots of other places and other kind of delta edges are lighting up as well. And I would bet on those also having very mangrove-like or likely mangrove ecosystems in those locations. And you can see there are other places lighting up. Let me flash back and forth. Other dense green vegetation, but really if we're talking about what's most similar to the mangroves at the location with the dot, it's those other places that are almost bright white in the similarity map. And that's just one small slice to really, again, show the power of this simple calculation and the global scale of the data set. Let's zoom to the literal other side of the world in Belize. So this is a view of Belize City and Turnof Atoll off the coast of Belize, another place where we expect to see mangrove ecosystems. We're still using the embedding vector from that point way back here in Vietnam. Let's generate the similarity map for Belize. And again, we're seeing those really bright areas where there are very likely mangroves. Now, this is fully unsupervised, so we aren't actually classifying anything. What we're saying is, based on the embedding space, these are similar locations in their embedded representations. And you could imagine taking this, adding a threshold, and you can start to map at a global scale where there are these mangrove-like ecosystems. N of 2 is a pretty low sample, so let's just add one more data point to really drive home and convince you, going same point from the Mekong up to the Florida Everglades. Again, we can quickly generate this sort of similarity map. And what really strikes me about this is, again, we've got lots of green vegetation, but we note that only some of it is showing up as most similar to those mangrove ecosystems. So you're really able to, again, quickly assess, explore the embedding space, figure out what's similar, what's dissimilar, and you can have as few as, this is essentially like a 1-point classification. So you need a single embedding vector, and you can compare it to every other embedding vector to get these sorts of views. I use mangroves as an example. I think they're a very powerful demonstration, but it's not just vegetation. It's not just forest or tree types. Here's another quick example looking at similarity for geologic features. So the top example is a biosphere reserve in the Sonoran Desert. That's actually a volcanic field out in bare land there. And if we make a global similarity map using a point somewhere, I think on the kind of right-hand side of that volcanic outcropping, we find that the most similar place in the world, it's, well, first of all, fairly distinct in the larger region in Mexico, but it is very similar to another volcanic field in Libya. So we're able to not just get vegetation types, you can see geologic similarities, and just a super powerful tool for exploring the similarity in embedding space. As a hands-on component, like the RGB app, this is an Earth Engine app that we've built to allow folks like yourselves to get in there and look at your own examples. So I'm going to pop over here and just show you very briefly. So this is the tool that I pulled all of the screenshots in those slides from. This is what I used to make those examples, but let's do one more again. So as I mentioned, I'm based out of New York City, and I like doing an urban example in addition to our vegetation and geology. Let's zoom in, and this part of New York, like Times Square, Midtown, picture New York City. This is that very classic New York area. And if we pick a point, so all I have to do in this app is just click, and you will see almost instantaneously start doing those similarity calculations. Now, I've been asked before, so you must be like caching this, doing this somehow. This is generated on the fly. So we're reading the satellite embedding collection, calculating those similarity scores totally interactively. There's a little chip at the corner here that shows you the exact field of view of the model. So this is 1.28 kilometers by 1.28 kilometers. So that's kind of the whole information you could imagine AlphaEarth Foundations actually got to see when generating an embedding for this location. And you get those similarity scores. I think it's super interesting then to say, okay, well, you know, in the Midtown Manhattan is less similar to some of the urban areas in New Jersey, or even over here in the other boroughs of New York. And zooming out, it's fairly distinct in even this urban area. But as with the mangrove example, we can do things like, if I zoom over in my similarity map to London, I can see that urban core, the taller buildings, the more densely settled urban areas here, similar urban structure is lighting up as similar. And, you know, again, just more data points. We can go over to Tokyo, other major cities in the world. And again, in that similarity space, we can see there's real structural information about these urban landscapes being characterized in the embedding space. And it's very easy to pull out into the single similarity metric using something like the dot product. Last thing I'll mention, so you may have played around with this app in previous presentations. We've also added more recently a year slider, so you're able to page through embeddings if you want to check something more specific in a different year. This won't preserve the points across years. So you're actually now pulling for that New York location, the 2023 embedding relative to everything else, but a little more flexibility if you want to explore the time domain. And this goes all the way back to 2017. So really fun interactive tool. I spend a lot of time playing around, just looking for those similarities in embedding space, and hopefully something that you'll get a lot out of as well. So going back to our presentation, I do realize I want to keep moving along because we've got a lot to cover and still a little bit of time, but apps are great. They help us kind of get our feet wet and see things in a very visual environment. But for us coders, always curious, how do you actually do this? What's under the hood? Now, the app code under the hood for that app is many lines long, and most of that is actually handling the visualization. But the core function is fairly simple. And so let's again pop over to Earth Engine, and I'm not going to live code this time. From here on out, I'm just kind of walk you through these scripts so you have a sense of what's in there, and again, encouraging you to go back and play with them on your own. But here we've got a script that is doing exactly what that tool is doing, exactly what we've been talking about all along. We take a point in Earth Engine. We have this concept of a geometry, so EE geometry point. We've entered a lat long. If you were working in the app, you could actually go over and in the pop-up for the location, it gives you the lat long. If you wanted to pull it into this tool and do more analysis with it, you could do that. But this is that lat long for my New York example. I'm getting our image collection. So here I've got the embeddings, that same collection ID we've seen before, Satellite Embeddings V1 Annual. I've pulled year out as a variable just to make it a little bit easier to experiment with different years. Instead of filtering by geometry like we did before to get a single location, here you'll notice we are just filtering by date. So the code is taking our year here. We are taking that year and concatenating the January 1st, adding 1. So now I get 2024 0101 to 2025 0101. And I've added a new function or a new call here to mosaic. So that's essentially taking all of those tiles for all of 2024 and we're stitching them into one big flat global image just to make it easier to display. We don't need to work on the individual tiles. Here we actually want that global coverage, especially because we're doing such simple math. You can run into trouble with this in Earth Engine if you're trying to do a lot of computation like our classification example with a full global mosaic. But for a very basic set of operations like the dot product, we can use the mosaic here. We need this bit on band names. So, and they're not really bands in the wavelength sense that we're used to thinking about, but the axes here, when I showed you in the beginning, the list of bands for each image, all of this call is doing, and I can actually adjust print so you can see this. This is just the names of the embedding axes, so you don't have to type them all the way out. So a lot of setup, really not a lot, just 6 lines there to get us set up. But here's where our similarity calculation happens. And this is maybe the most complicated version of this, if only because we have to use a sample. And so I won't get into the details here. Just trust me, this is the most efficient way to do this. I'll give you some resources where you can learn more about the implementation in a sec. But what we're doing is we're taking that mosaic, so that big flat global layer with all of the embeddings for 2024. We are using the sample function in Earth Engine. So this is allowing us to specify a region, in this case, our point of interest. Our scale here is 10 for 10 meters, since we want to sample the embedding layer at its native 10-meter resolution. We're then going to take that sample. We're going to turn it into an array just to make the math a lot faster. So you can imagine what we have at this point is a vector of the embedding values for each of those 64 axes. And then here's that dot product calculation. So we've got our vector for our sampled point, and then we are just going to multiply it by every other embedding vector. So we've got our image, we take that one sampled vector, we multiply it by every single other pixel, we sum up the product. So we go from 64 for each Each location collapsed back to one number, which is our cosine value. We need a first here just to get the shapes of things right. And that is our dot product. That's all that's happening under the hood of that app, wrapped in a bunch of UI goodness. I've got a palette here mimicking, I can't remember if it's magma or plasma, but a very nice color shading just so that we can visualize those similarities. We're putting them on a scale of 0 to 1. If you remember our dot product, 0 would mean that the embedding vectors are perpendicular to each other, where 1 means they're perfectly aligned. So 1 is on the bright side, the brighter things are, therefore the closer they are. As soon as you're hitting perpendicular and beyond, they're getting much darker in this visualization. Adding my point here to the map just so we can see it, and our similarity layer underneath it, and we get essentially the map that we saw in that app, but you've reconstructed it yourself in code. And so that is what's under the hood of the similarity search. If I go back to our presentation here, I've got a little view of that. But again, you can use this to compare things spatially. So we're all operating within a single year. Now, similarity search, since we're just working in vectors, doesn't have to just be in space. We could also think about this as a powerful tool for comparing embedding vectors for the same places, but in time. And this is actually a simpler calculation, but I think nice to kind of step through it after you've seen what this looks like in the flat spatial view. So when we're talking about similarity in time, as I mentioned earlier, our similarity in space, we're taking a sample and we're comparing that sample, that little blue square, to all of the green squares. So every other vector in that same map. For similarity in time, what we want to do is we want to take 2 of those annual layers and we want to compare the embedding vectors for the paired locations across them. Same calculation, but now we're working at kind of full image rather than point to image. And again, before we go into the code, I just want to show you where we're headed, what this looks like. These examples are pulled from the Central Valley in California. For those who may not be familiar, this is a very mixed landscape. It is kind of the agricultural center of California. So we've got kind of the agriculture in the middle. We've got mountain ranges on the side, and city of, I believe, Sacramento down there in the lower right corner. And this is a very dynamic landscape. So we've got things going on like forest fires and timber up in the mountains. We've got a lot of reservoirs, so we can start to think about applications for tracking water resources through time. Again, that agricultural areas. So we've got lots of fields that are changing in terms of what's being planted, when it's planted, the condition of the crops. And with the urban landscape, we're going to see some suburban development. And if we go back to that sort of RGB view, so picking 3 axes, just a very colorful look, let's just think about the 2020 embeddings for this landscape. And we get this very pretty rainbow map, forgetting what the color combination is, but we get a lot of variability across these different types. And if I flip just these 3 channels between 2 different years, and we go back and forth a few times so you can kind of look at what's changing, you can see how dynamic things are even in just 3 axes of the embedding space. We're seeing, the impact of a large fire coming through up in that green square. We're seeing some changes in the reservoir level in the kind of blue tones there. We're seeing fields kind of shift around. Expect that to be, again, something to do with timing and what's being planted. And then those green patches showing up in the suburban development example. That's the expansion of, I think it's a suburban development right at the fringes of the city, kind of moving into the agricultural area. So just in those 3 channels, we're seeing change, which is a good indication that when we use similarity to look across the full embedding vector, we'll be able to capture that change even more clearly using all of the embedding information. And this is what we get when we apply our similarity dot product between those 2 years. And so in this map, things that are brighter are actually more deviation, so kind of the opposite of what we were doing in the more colorful spatial similarity view. Here, if it's bright, there's been a big difference between 2020 and 2024. And things that I like to call out here, if you're looking at that forest fire and timber example, you see these kind of tiny little patches within that larger bright area. Those are actually existing timber harvests within a burn scar. And so the area was already burned to the ground, or it was already cleared before the burn came through. So those are showing up as dark because there's not as much change versus kind of the brighter areas that were burned and are showing vegetation loss. Kind of after there was vegetation there when the fire came through. The water resources example, similarly striking. We can now see a channel coming through, and that darker tone is things that have not changed. So you can imagine in a drier year, which I believe was I forget which of the two is the drought year, but we're seeing that kind of stable area of water as well as the little stream feeding it very clearly versus the area that has fluctuated between the years as that brighter, bigger difference in the embedding vectors. Agriculture always shows up in these dot product comparisons as all over the place in terms of change, and that has to do with both what's being planted, so the actual spectral signatures, the texture metrics that we're getting out of, or texture information from the radar signals, the climate information, and the phenology. And so even if it's the same crops but planted and harvested at different times, you'll start to see differences in the embeddings and how they've encoded that phenology, which will then show up as differences in the dot product. So again, this is unsupervised classification. We're not ascribing any meaning. These changes can be all over the place, from actual land cover change like suburban development or water level changes, through to just changes in phenology or changes in large scale weather patterns. You'll notice there's some kind of lighter tones to the left side of the large map. And some of that is just a product of we've got different climate precipitation regimes, drought years, and that will affect the embeddings. Though to move that whole embedding vector in a really large way, you tend to see a very high a signal when it's like a more physical change versus the kind of larger scale weather context. So that is my visual example. Just like the spatial similarity search, though, I want everyone here to be able to implement this themselves if they want. So I'm going to hop over. That code link is in the presentation. These are the exact same sites that I was showing. They're even colored the same for convenience. So we can look at here over in California, our study area, just to walk through the code before I run it. So we're loading our data set. Now, instead of 1 year, we actually have 2, and I've noticed I put 2018. Let's change that to 2020, so it totally matches the example, though 2018 would longer time range to hopefully show you some more change. We're going to repeat our kind of process from the first example, looking at the code editor where we were filtering dates and bounds. Here, we're going to take our first image. We want to filter to our first year. We're going to filter on our geometry. In this case, I'm just using one of these points. We could merge them all if they were more disparate. We could draw a bigger box if we wanted to, but just for simplicity, we're picking one geometry to filter on, and we're just going to grab the first image. So we actually have an image as opposed to an image collection. If you just ran this without first, you'd end up with an image collection with one image in it. But our math all operates on images, so we need to pull out the first. We'll repeat that again for year 2. So same exact code block, except here I've substituted year 2, which will give me the 2024 embeddings. Similar to what I showed again in that visualization example, here I've pulled out some visualization parameters. So when we look at things on the map, and we can see, if we want to go back to that color combo, that was actually axis 1, 16, and 9 to get those very pretty rainbow maps. That same scaling, we'll reuse these visualization parameters in our map add layers just to create those colorful visuals to kind of give us a basis to look at things before we get the single similarity metric. But here in 3 lines that could actually be collapsed to 1 is the math. So dot product, the equation looks complicated, but it's again just image 1 multiplied by image 2. So we've taken the product element wise across those embedding vectors. And then Earth Engine has this concept of a reducer. So we reduce using the sum reducer, and that gives us our dot product. And I will just run this quickly. to prove to you, you can recreate exactly what you were seeing in the slide deck. So if I'll turn these off and back on, there's our 2020 embeddings for the whole of that Central Valley tile. Here's our 2024 RGB, just showing those few axes for some context. And there is that similarity map. And just again, just to show you, I think this is so interesting. We're looking at, here's our harvests that were already apparent, those kind of warmer tones, those little leopard spots in 2020. We'll turn on the 2024 layer and you can see the whole area is now affected, and it's this larger burn that came through, burn scar. And when we calculate our similarity, we'll see that those little places that were patches in the 2020 layer are very, very dark. So they stayed similar. They still are bare. The fire didn't affect them very much, versus that larger context where we are seeing the impacts of that fire on the vegetation. So really powerful example, really simple math, but gives us a way to use change in embedding space, and all without supervision. So we're just using the embeddings themselves and comparing them to look in the embedding space for information content. All right, so if that's temporal similarity search, I'm going to close out this section with a few more resources. If you're like, this is amazing, I want to learn more, the first thing I would like to call out, so I mentioned the Earth Engine catalog page. There is a version of this script, just fewer geometries, but same general study area right on the catalog page. So I will even just do this so we've all seen it. If we go into the Earth Engine data catalog, there's that description. But if I scroll down, you see this explore with Earth Engine. There is that script. You'll see the point, the data set, the filtering that we did, the visualization. And if I click open in code editor, I can come over here and it will actually load. Again, it's a very similar version of this script where you can look at change through time. And so if you're like, away from the presentation, want to demo something really cool using the embeddings, you can always get back to this just from the Earth Engine catalog. I also want to mention that we do have a series of tutorials on the satellite embedding data set in our developer materials. So developers.google.com/Earth Engine tutorials. And we have tutorial 5 is all about similarity search. These were written by Ujjwal Gandhi at Spatial Thoughts. He gives examples of how you can use multiple points instead of just one, discusses a little bit about resampling. So being able to rescale the embeddings to other resolutions and conduct similarity search over a larger patch. So if you really thought this was cool, you want to dig in more, highly encourage you to visit the tutorial and work through the exercises there, which cover things in a lot more depth. Wrapping up our section, so for our similarity search, this is a way that we can compare full embedding vectors to assess distances between them or angles between them in embedding space. Just like you would subtract image bands, this is our vector math to do multi-point comparisons, whether that be spatially or temporally. This is all done on the fly in Earth Engine. This is Earth Engine's sweet spot. We're doing band math. It happens very quickly, so you can really easily work with that full global data set and explore patterns both locally and around the world. Keep saying these are simple operations. You could think of just adding a simple threshold on similarity to say, here's the most similar things, let's classify them together, like the mangrove example, or dense urban centers, like the New York example. Or in the temporal, you could think about, high dissimilarity is now a very quick unsupervised change map that you can use to start to flag places that may have changed between years. So really simple operations, no training data required. Again, you can do this in space or time. And we haven't talked too much about this, but the embeddings are also designed to be pyramidable. So Earth Engine operates with image tiles. Those who've used it for a while, it's all based on a pyramid structure. So aggregating up as you zoom out. Embeddings are the same. They are linearly composable. The way we construct the embedding space means you can average embedding vectors, and the result should be semantically in between the two. So if you average a forest vector and a water vector, that should be close to the position of something like a forested wetland, just to give a semantic example there. So if you want to do your similarity search, resampling embeddings to 100 meters, a kilometer, an entire degree cell, you can do that, and you should still get a meaningful output, even though you're working at those coarser resolutions, which gives you that flexibility between that 10-meter pixel and any larger quote unquote patch scale that you would want to work at. Whew. So that's been a lot.
Yes, Valerie, it was a lot. Very super interesting. I have just two quick questions to you because we're asked, you already say that, but
like I said, we rescale the images so that they're back on that -1 to 1 scale and floats, as opposed to the byte representations that you have to rescale yourselves. So if you can work in Earth Engine, the satellite embeddings were built for Earth Engine and designed for easy integration with the Earth Engine compute platform and API, but you have that cloud option available to you now.
Okay, thank you. And then, if I'm not wrong, the embeddings are also available in the Taylor geospatial engine.
Yes, that's a great point. There is also a copy, Taylor Geospatial. We worked with a bit to get them from the cloud copy, and they're hosting their own version. So that's yet another option. I think they've done some different structuring there. So you've got lots of choices now, whether you're working, fully outside of cloud, in cloud, or in Earth Engine. Embeddings are available.
Exactly. So you have no more excuses. You can start using the embeddings. And thank you so much. Thank you so much. It was very clear, very nice presentation. There is one more question, but we'll ask at the end. Also because now we want also to see what Kathleen wants to tell us.
Caitlin, did you want to jump in on anything, or should I proceed with the classification?
Yeah, I think Valerie has a bit more applications for us, so I will go quiet again.
Okay.
Yeah. All right.
So please go ahead at this point.
All right. So one more big chunky section here before we get into more Q&A, and keep hearing from me on supervised classification. So everything I've shown so far has been unsupervised. It is just purely working in the embedding space. But really what we build embeddings for is not just visualization and unsupervised comparison, but bringing labeled data, and not just any labeled data. Labeled data is hard to collect. If you've worked with doing any sort of your own annotation, getting it in volumes enough to train a big deep learning model, or even a big classic machine learning model, you've got to collect a lot of data. And so the goal here was, by producing this very compressed, very clean representation, we could accelerate the classification process and allow you to make accurate maps, but need less data to do it. So you don't need, millions, billions of training labels. You don't even need wall-to-wall annotations. The embeddings are compressing space and time. So you can take simple points with a small number of labels and start to generate maps faster than ever before. And let me tell you more about how we're going to do that. So for those who may have taken Earth Engine trainings before, supervised classification is effectively EE 101. This is something that we've been teaching in Earth Engine for ages. I've got the little screenshot to the side there, but we've got all sorts of materials on supervised classification, working in that case with raw image input. So a lot of our examples are built on Landsat or Sentinel-2, where you're processing images. You've got to pick which images you want. You've got to mask those, all those things I showed in that first visual you like to show with all of the different processing options. So cloud masking, atmospheric correction, compositing, or other feature extraction. And then you finally, many lines of code after kind of starting with your Landsat or Sentinel collection, get to being able to classify. Embedding should make that a lot faster. And here I've got kind of the general process. If you've never done a classification before, or just even a refresher, really simple in 5 steps. We need some sort of training data. We need to either collect that ourselves or get that from an existing source. We need a classifier. So what are we actually going to use in terms of a model? And here I'm very specifically thinking of Earth Engine classifiers. So classic ML, I'll get into more in the next slide, but that's got some parameters. You're going to have to set them, but this is just a classifier, not building like a whole model on top. This is really basic ML. We need to train that classifier. So we need to take our label data and our features. In this case, we're going to be working with the embeddings in order to train the classifier to make new predictions. And then we want to take that trained classifier that we gave the labels to and apply it to other images or feature collections, equivalent to like vector data or row table rows outside of Earth Engine. And finally, it's not just enough to make a pretty map. We've got to do something to quantify how good was our classification using some flavor of independent validation data. And while training you to process raw satellite imagery might take me a full, half day or even full day workshop where we would go through all of the steps, with the embeddings cutting out that whole first part of the processing chain, I'm going to show you how fast it is, how quick and easy it is to build a classification workflow in Earth Engine with the satellite embeddings. So those are our basic steps. I did say we've got kind of Earth Engine classifiers in mind. If you're working in the Earth Engine API, we've got this great list in our classification guide of all of the different classifiers that are available. I love this table. It shows you which ones do classification versus regression. Some have outputs in terms of probabilities. So if you don't just want the final label, you actually want the probability of different classes, you can do that. Different options for regression, but mostly to show there's a lot of different options here. Today, we're going to be working with random forest, since that one's very familiar to most folks, but we've got support vector machines, gradient boosting trees, classification and regression trees, distance classifiers, maxent. So a lot to experiment with here. And the general workflow across all of these will remain relatively the same. Just a few options get changed. And we don't, unfortunately, have time for everyone to collect their own training data set. In fact, that's usually the hardest part of all of this. For our demonstration, we are going to use the one of our classification evaluations from our AlphaEarth Foundation evaluation data sets. And in fact, this is one that Caitlin was a big contributor on. So GLANCE is the global land cover estimation data set. Caitlin and team kindly made this data set freely available. They've got a great paper in Nature Scientific Data describing the data set. And for AlphaEarth Foundations, we wanted to evaluate our model performance on the sorts of tasks we expected people to be using the embeddings for. And so you'll see GLANCE in that bigger table on the right. That is the full list of our evaluation data sets that we've processed into our own format in order to run our assessments. I'll show you a bit more in the next slide. But just to point out, of the many things we evaluated, GLANCE is an example of land cover classification. It has global coverage. The labels were designed to be applied annually. And there's 11 different classes. And in total, we filtered the original data set to just focus on some specific sources, but we have about 34,000, almost 35,000 points in total. And to the claims around, you need less data than ever before, we are only going to use 300 points per class in the experiments, in our evaluations that we ran, and in the tests we're going to show today. So again, just to show our version of this data set. So this is the The breakdown, this is covered in the supplemental materials. So this is table S1 or S10 from our archive paper showing the glance classes and splits. You'll see we have 11 classes labeled 0 to 10, so always indexed on 0. We have a numerical integer label. We have a human readable label named, because that makes it a lot easier to go back and forth between the numbers and their class descriptions. We've split the data set so that each of the classes have a randomly selected 300 points allocated to training. Now that's, think 300 points per class globally. This is a very small sample, so only 300 water points to train a water class to map the entire world. So very relatively small sample sizes than you might normally see in like a big deep learning or production operational land cover mapping exercise. What wasn't in our train count, which is intentionally balanced, our evaluations also included a bunch of KNN, so we really wanted to make sure we had equal representation across classes. Everything that wasn't allocated to training was allocated to test, and you'll see those test sizes vary quite a bit, but we always have at least a few hundred points in our test set. And the little maps on the right there show the distribution of points by their splits, just so you can really see we are getting global representation for the different classes, and that test set's a lot bigger than the train set. Just to call out, I don't know that everyone necessarily knows this, the CSVs and documentation for all of our evaluation data sets that we used in our development of the model are available on Zenodo. So you can download this data set straight from CSV, as well as any of the other data sets that we used. These are processed versions of these data sets. So we did things like deduplicating if there were multiple observations for time periods, so we were only assessing each location once. We guaranteed that observations or points in the evaluations are at least that 1.28 kilometers apart, so there's spatial separability to reduce autocorrelation. So there's not a one-to-one match necessarily with the source data sets, but this is a filtered version that we use. So it works really nicely for the example we're going to jump into, because we know that these are well-distributed, well-cleaned versions of the data sets that we derived them from. So that's the glance data set. If you were to download the CSV for the glance data set, you would see something like this. This is, again, our processed version that has minimum viable information for an evaluation task, which in this case would be running a classification and assessing with running a classification with the training set and assessing on the test split. You'll see again that label name, so the actual human readable name for the selection of rows. We have a valid time start and valid time end. Now, if you remember way back in the beginning when I was saying the model summarizes over a given period, when we are assessing embeddings, we wanted to match our embedding period to the period over which the label was valid. And in the glance data set, we actually have a mix of different years. So you'll see those timestamps vary. These are all in milliseconds since epoch, so they're not super readable, but you'll at least see the numbers vary, and they always correspond to the start and end of a year. But this will be important when we go to pull the embeddings for these points. We'll say more when we get into that. A couple of grayed out columns when the model is generating predictions. We don't just generate for a valid period, we also provide what we call a support period. So the model has access to more information, more temporal information. So you might be predicting for a single day, but the model will get to see a year of images to predict for that day. We don't really use it in this case so much. The support period's the same as the valid period for these annual examples, and that's mostly in there for documentation. We are only operating with points here, so we just have an X and a Y, a lat long, in decimal degrees. We need a machine readable label, so again, label names are great, but we wanted, or we needed to have a integer, or if we're working with measurement data, a float value that we can actually use in training our classifiers, and these are sequential integers for classification tasks, which means pretty much ready to go in anything you want to do in Earth Engine. And importantly for this, we have our train test split. So the data set's already been batched into 2 partitions. And again, grayed out, there's a shard column if you're working with larger data sets can be helpful to partition it. We added that in there. We won't be using it today, but we will be using everything that is shown not grayed out in order to train our classifier. So the first thing I did after taking that CSV that was available on Zenodo, you can imagine this is your own data set that you've processed into a form where you've got integer labels and you either know what year they correspond to match with the embeddings, or you've added a timestamp like we have so that it can vary per row. And we've ingested this as a feature collection. So this is that same CSV. We've imported it into Earth Engine, and we see this little pop-up view. We've got an asset, as they're called here, which is essentially a table with all of the rows and geometry information. The asset I'm using today is publicly available. We've shared it with everyone so that you can rerun these same code examples yourself and play around with them, also to give you a sense of how you might format your own data to make this as easy as possible. So once we've got that label information, so we know what we want to classify, going back to our 5 steps of classification, the next thing we need to do is pull the feature vectors, or in this case, embedding vectors, associated with each of those labeled points. So let's go over to the code editor again. And as we did before, I'm just going to walk us through the examples. So we have a collection of point locations. In this case, it's called Glance Demo Dataset. That's exactly what I just showed in the last slide. We're going to pull our embeddings again. This should look fairly familiar, but instead of operating with a single flat image the way we had been before, we want to pick a single year. This is perhaps the slowest but most general solution to embedding samples. So I'll say up front, this isn't the only way to do it. It isn't necessarily always the best way to do it. But given a data set like Glance, where we want a different year for potentially each row in the data set, each label, we need to look across each of the rows and say, what year are you for, and pull the correct embeddings. So that's effectively what this sample embeddings function accomplishes. So we apply this, it happens down here with a map in Earth Engine, but we essentially run over our entire point collection. Each row, as I showed in the slides, is one of these labels with its associated columns. We are going to filter the entire embedding collection to just that point location, just like we did for our dropped points in the previous examples. We're going to actually get the start time and end time that I showed for that particular row. So we've now gotten a specific location, and we've gotten the corresponding year that we need to filter the collection for. We're going to mosaic it just to make sure we've got a nice flat layer. This shouldn't actually do that much, but it at least flattens everything out if we've got right at the edge of 2 tiles. And then here's the most important bit. We're going to take that embedding image associated with that label. We're going to sample the particular point that we want. So we've got our label geometry. We're working at a 10-meter scale. We want to keep our output geometries. In Earth Engine, you have to set this to true if you want the resulting output here to keep the lat long information. Got a little bit of logic just in case that you come up with a null answer that we're going to make sure that we don't hit any errors. But all of this bundled up to effectively iterate over each row in that table, grab the associated embedding image, sample the vector for the specific point of interest, and then produce a new collection with those embeddings. So if I click run here, we'll see here's the actual points in the Glance data set being displayed on the map. I have a little map add layer points up here that's causing that to happen. But really the important thing is you'll see this tab over here with tasks has lit up. So this is my export with embeddings. And if I were to click run here, that would actually run the task to do the sampling. Now, all of the other examples I was showing, we did this live. So we were just working with Earth Engine. Everything was being computed in real time. For this actually takes a little while to iterate over all these points. And in fact, the way we're doing it's like the slowest way. There's imagine if you have labels for a single year, you could get 1 year of embeddings and those points, and you could do a single sample, and it would be a lot faster. But this takes, I think, about an hour, 45 minutes to an hour to run over those, like about 35,000 points, and we then export that to a new feature collection, a new layer. And I'm going to go back over here, kind of my magic, pulling it out of the oven, but we've already done this for you. There's another data set called Glance Demo Dataset with Embeddings, and just to show you, here is the kind of pop-up view of that asset, where we actually have the embeddings appended. Going to switch back to Earth Engine just again so that you can see what's happening. But if I open the information box for the embeddings, we've got the asset details still loading for me. It should be here any second. Well, not sure what's going on there, but this is why we have a foolproof slide example. If I were to scroll over in this window, you would see that we have the label information and all other fields that were in the original copy of the data set. So our label name, the split, all of that. And so here to the interesting part, let's actually look at how we would do a classifier. So 21 lines of code, including blank line spaces and a multi-line palette. So this is so concise, no pre-processing. I am really just loading the satellite embedding image collection. I'm getting that glance demo data set with embeddings. I told you we've already appended the features, so that's all there, ready to be trained on. In this case, let's say we want to make a map for the year 2024. So this is not necessarily what we're pulling. This is what we want to apply to. So we're going to get that ready by saying, okay, let's filter again by year. I've picked a single point over here in Wisconsin just as a quick demo example, but that's where we want to apply. And here is the rest of the classification workflow. So I've got my training. I'm going to take my label data set. I'm going to filter it so it's just the points in the training split. So I'm using an Earth Engine parlance, it's filter, and then we're going to apply a filter equals, and we want to look for where split, one of those columns we have, is equal to train. We now have a data set that is just our training points, so the 300 points per class. If we want to convince ourselves of this, we can print train. We'll see if it actually does this. Given the size of the collection, it may not. So in fact, just in the interest of time, I'll print train size. So this isn't the full data set. This is just the we've got 300 points per class, 11 classes, so 3,300 points. We can then take that training data set, and you'll see E classifier, smile random forest. That's my instantiate a classifier step. We have 100 trees, so mentioned in that overview, we need to set some parameters. More trees, more memory, so there's always a balance in Earth Engine, but 100 is a pretty decent starting point. So here's our 100 tree classification. We are going to put as our training input. So here's where we actually train the classifier classifier.train. We're going to input our features, our training points from line 7. Our class property is going to be label. Remember, that's the integer label, not the label name, because we need it to be an integer and a continuous sequential integer. We need for our input properties, this is the features. So like we did in the earlier example, we're going to take our embeddings and actually just get the band names. So we have that list of axis names without having to type them all out. So quick shortcut for that. We're going to set our output mode here to classification. We could also set this to say multi-probability or probability if we wanted to get class probabilities. Today, we're going to keep it simple. Winner takes all. We want the top label. And I should also note, for those who are newer to Earth Engine, we have a great tab over here for docs. And if I go into classifier, if I wanted to know more about some of these functions that are being called, for example, here's our smile random forest. You can see the main required parameter is the number of trees, but I could adjust variables per split, the leaf population, bag fraction, all sorts of other things. We also, this is the train main function we just talked through if you wanted to read more about the arguments here. And then finally, that set output mode, you can see some of the options depending on the classifier, going back to that nice table I had in the slide deck, whether you pick classification, regression, probability mode, and it's going to depend what classifier, which of these is available, but defaults to classification. I put it in explicitly here so we could see it. And now we have a trained classifier. It's that easy. So just a few lines of code to train the random forest. And for our result, what we're going to do is we're going to take that embedding images. It's a little broken up in the script, but we've got our 2024 embeddings for this location. And if I then apply the classifier, so classifier, this is our classifier object that we've instantiated, our random forest. Classify is actually applying it to, this is an image here, and that is our result that I'm going to add to the map using a nice color palette here. And if I zoom in, I mean, this is cached because I have run it a few times before. Earth Engine does save some computation, so it won't be as slow to load every time, but it really does happen in a matter of seconds. And we get a map, not of the entire world. We would probably, I'd say, almost certainly hit a memory issue if we tried to run this 100-tree random forest for every 10-meter pixel in the entire world, or even just at a very large view shed, which is how Earth Engine actually works. But we are able to look at our results again in real time, and we have assigned labels to each pixel. If I go to my inspector tool, you can actually look at the pixel values. So you need our little key, and I'll show that in a second. But this is our classification layer. If I kind of swipe back and forth, we can see, you know, river areas seem to be showing up in blue, the water class. Red here is our urban class. So we're seeing kind of roads and city centers. Yellow is an agriculture class. You can see the agriculture is popping out. We've got some different greens showing forest areas. And so we have trained now on our small glance global data set. We've trained a random forest on it. We've taken that random forest, we've applied it. So we've gone through the first 4 major steps in classification just in the past 15 minutes here. And I should also say, the script is pretty cool. If you're accessing it, you can easily, if I wanted to say, delete my geometry point here and not work in the US, let's say, maybe I'll come down here into South America and let's see what happens. I'm just going to pick a random additional location, add a new point, and see how fast it delivers. All right, brand new classification, new area. And again, on the fly, this is being classified as a grassland and shrubland are the colors we're looking at. We've got that dense forest. I'm seeing some interesting little patches here. And lo and behold, zooming in, the embeddings and the labels associated with them are actually picking up on what looks like some clearings in the base map. So you can take this quick demo example and make yourself a glance classification for literally anywhere in the world. Let's just do one more. If you're following along, feel free to pick anywhere that you're used to working. I think we've done a lot with Geneva. So let's go over here and try a different city than kind of rural United States. And I'll drop one last geometry point, run this again. And there we go. We can see the city is being classified as urban. We've got the water features clearly showing up in our water class. We can see some open lands, forest patches. And one thing to really note about classifying with embeddings, if you've classified raw spectral data, you get a lot of noise, a lot of speckle. Here we've got very smooth outputs because we have all that spatial, temporal, multimodal context, and we have a really clean embedding space. So in the interest of time, I'm going to hop back over to the presentation. Here, if you're looking at the glance maps, we've got a little legend to help you discern some of the colors. The code is kind of shown visually as well, but feel free to keep experimenting with this example and this data set. This is available to you. Last little piece of step 5 in classification. We don't want to just trust the map. We actually do want to go and do some sort of error assessment. I'm going to go through this super fast, but again, code is all here. We've got that same script I just looked at, but here I've added just a few more lines. I have created a new variable that takes the test split of our training data set. So just as I pulled out the training split, and rather than call classify now on the embedding image, so classifiers work on both images and feature collections, I can call classify with my trained classifier on my test labels. So one line of code, I've now applied that trained classifier to just the table data. I had no images involved. This is just the points that were in the test split. And then Earth Engine has a function called error matrix. Let's go over to the docs just so you can see where it is. So error matrix takes the actual values. So in this case, this is our label field. When we ran classifier, it added a field called classification. And let me just show you if I print test, and I'm going to limit, which will give me just a small set of the full examples. Getting an error. So let me see if I can do it with first instead. There we go. So where before we had the 64 bands and then just our original, this classification field has been added once we ran classify. Test that with code to prove it to yourself, but take my word for it. And we get our error matrix by comparing our original label with the classification label. And then we have a bunch of different functions available to us. Earth Engine, you can do the F1 score, we can do overall accuracy, producers, consumers, and if I run this script, and we've got the little visual back for Wisconsin there, I've got this set up to print this to the console. See if I actually get it to run. I'm getting a little bit of memory errors. As you see, when I refresh, I can usually get it to run Earth Engine's shared resources, and sometimes it can be a little hit or miss on those memory overflows. But the important thing is, I think the easiest thing to look at, here's our overall accuracy. So we've got about 67% overall, so unbalanced test split, but kind of a good representative sample with a large number there. We can get the per class F1 scores. So see things like, I believe class 0 is our water class. We're very accurate. Class 2 is, if I can get back to my, so our soil class is a little less accurate. Pull up the example here. And again, you can look at those lists again for producers, consumers, which is a list of a list, and really kind of dig into the accuracy very quickly, very easily. And the script is under 30 lines of code with all of those metrics, with the training, with the filtering. And so a full classification workflow in Earth Engine on the fly, start to finish. And you could be doing this in, under an hour. Really even under a half hour, as we've shown today, to get started. So that concludes our demo sections. I do want to flag again, we have a full tutorial on supervised classification with satellite embeddings, different examples than I showed today. So totally new material prepared by Ujjwal Gandhi at Spatial Thoughts. The link is there. I believe this example is on mangrove classification and works with random forests as well. Also want to point out, we worked with categorical variables just for simplicity, and that's a lot of what's available in terms of annotation data sets. Looking at that list of classifiers, you can run classifiers in regression mode if you have continuous measurements. Here's a little example shown here. We did some interpolation with about under 1,000 samples of plant foliar measurements from the NEON network and made a global map, again, just as fast as we made those classifications. So you can do this and extend it to regression, same basic idea, same basic workflow, just different classifiers in different modes. And in summary, you can use supervised classification, use embeddings in place of standard inputs to make your classification regression workflows much, much faster. This is a lot faster than going back to source imagery. Embeddings have wall-to-wall coverage, no cloud masking, no pre-processing, no feature extraction. We did that all for you, so you can just start with the embeddings and build on top of that. It's a relatively low noise feature space. The constraints I talked about way at the beginning help design this space to work with simple classifiers like decision trees, clustering algorithms. You don't need more deep learning on top of it. Now, of course, you can build whatever models you like on top of the embeddings, but really you should be able to work with what's already in Earth Engine and leverage those compute resources to make things go super fast. You should get good performance with few observations. I hope my glance demo convinced everyone, just 300 points to make pretty reasonable looking maps globally. But that said, if you do have super large, very high quality label or measurement data, you should get even better performance. So right now, the bottleneck shouldn't be your deep learning feature extraction. It should be the quality and quantity of your label data. So put that effort into collecting good labels, cleaning those data sets. I'm sure we could do some processing to optimize performance even more than our 67%, just kind of going in cold. And having this global embedding data set plus the power of Earth Engine makes this sort of scaling so easy. So making maps in seconds instead of having to download and set up environments. It's all kind of at your fingertips with Earth Engine and satellite embeddings. I want to make sure we have at least a few minutes for questions, but just to show a few examples, it's not just us making example maps for show. We've seen embeddings being used in the real world. One of our most exciting from back in September, the USDA NAS released their first ever Hawaii cropland data set. So really rare classes, distinct crop types for a very hard to map part of the world, lots of cloud cover, lots of topography, and they were able to produce crop specific data at a 10-meter resolution for the first time by using the embedding data set, and did this just like weeks after we released the embedding collection. We've also seen published studies coming out. So to the point about what can you map, it's not just land cover. We've seen work on urban air quality, so predicting urban air quality constituents, so PM 2.5, things like that, relating the embeddings to those measurements. Groundwater fluoride, so I found this fascinating, being able to predict the distribution of groundwater fluoride using the embeddings for water management and getting improvements of 13% in their error rates, and even not just like classification variables. Some folks are working on yield predictions with the embeddings, so corn and soybean yield as opposed to just saying corn and soybean. So tons of applications. If you look at what's citing the paper, you'll find all sorts of interesting use cases and really diverse, because this was designed to be a general purpose Earth observation data set. So I'll leave you with a few points. AlphaEarth Foundations is a virtual satellite that's summarizing surface dynamics in space and time. We were able to, as I hope my examples have shown, and the examples in the literature continue to prove, that we've learned meaningful patterns across data streams, and we've generated precise embedding vectors, and we can do this for any place and any time. Again, the model can produce those embeddings over any summary period. We're looking more into that capability more and more, but for now, we've got the annual embeddings out there to get you started. These embedding outputs were really designed for practitioners, folks like you. Hate to say it again, but it's sort of like an AI-powered image composite. You get a compositing period, and you get these features that you can plug in for classification, regression, change detection, and all sorts of related applications. And we think of these embedding images, why we call it AlphaEarth Foundations. The embeddings are a foundation on which many applications can be built. And with that, here is a list of resources. These are in the deck. If you wanted to learn more about the cloud offering, read our blog posts, get back to the data set, the paper, just a quick short list. And again, those tutorials are really awesome if you want to go all the way from the start or dive in at any specific application that interests you. With that, I think we still have some time for Q&A.
Thank you, Valerie. Thank you so much. I feel like the future of geospatial is already here. Perhaps this would be a good moment. I could also call on Catalin and Professor Maria to join for a short question and answer session. We have an incredible number of questions coming from our viewers. I can start with a very quick one here from Ali Reza, who's wondering, some of the sensors in the training process have latitude limit, like GeoAI, which is at minus or plus 51.6. And the embedding has no limit in these latitudes. How does the model deal with these missing data? Either to you or Kathleen, whoever would like to take it.
I can, Caitlin, do you want to take this one?
No, you've got it, Val. You're the expert.
So for missing data, that is one of the benefits of how we structured the model in terms of inputs versus targets. And so our input data sources, we expect to have more continuous coverage and more complete views. Whereas when we're reconstructing, we can mask. And so for GeoAI, for example, we are only reconstructing the places that we have information. And we basically tell the model, we don't care about where we don't have observations. So it allows us to use those sparse data sets. It allows us to use data sets that have different coverage, and we really adapt for that in the architecture, and again, gives us that flexibility.
Fantastic. Over to you, Maria, if you want to take the next one.
Yes, I have a question by Mohammed Ammar, who is one of my students. So I'm very happy that my students are attending. And he's asking, can we average the pixels of multiple crops and get a single pixel representing all the crops? The average, good, but at this point I want to add something else, which is the dispersion. So how to compute the average and also the standard deviation.
So I think I mentioned the embeddings are designed to be linearly composable. So you can take an average over multiple points, over an entire polygon, over a larger regularly spaced patch. So absolutely, yes. And we've actually seen folks, particularly those looking to resample to coarser resolutions, find that they have greater success doing searches and matching, not just based on an average, but also include standard deviation. So variability within the area. The less variable, the embedding should be relatively similar for adjacent places or crops that are very similar, but that standard deviation is a nice way to capture variability. And 100% yes, you can calculate both when you're trying to summarize multiple pixels.
Yeah, and probably when we compute the average, so we summarize, we have to normalize it. Because if we want then to study the similarity with respect to other parts, the embeddings are normalized. And so we have to normalize also the average.
The average is, so it should still be normalized on a unit length. They're already normalized, so you're averaging, you should still be on that -1 to 1 scale, and nothing should be greater. So it's already baked in. We handle it with pyramiding as well. You can get a little bit of variability, mostly due to the quantization. So when we've quantized, variables are quantized. When we unquantized, you might see slight differences from a perfect unit length. But generally speaking, you shouldn't have to do any normalization. They should be pre-normalized.
Okay, thank you. And then I leave you, Rohini, to ask other questions.
Sure. Here's quite an interesting question, which I also had in my mind from Yung Hyun. Aside from the annual data sets, could you provide a timeline for when the monthly and daily data will be accessible? He's quite interested in knowing the future implementation plan and what's coming.
Yes, this is a capability of the model that we've heard a lot of excitement about. We are currently trying to understand the demand and how to best surface this capability. So we have a tracking bug. We could probably get a link in the chat, or I can add it to the presentation afterwards so folks can see it. But we have a data set request where we're asking folks to register interest in what they would use other embedding, or monthly, daily, what cadence would they want things at, and what applications would that unlock. And we're using using that to help understand, is this a different data set? Do we want to have some sort of ordering system where you would be able to generate your own? So we are actively trying to understand what would best suit folks' needs. So the more we hear about those needs, the more we can ensure that what it ends up taking as a product shape will work for those who've been interested. So I'll add that to the presentation right after this, and you'll be able to find it. I'll put it in the additional resources slide. But please register interest or reach out. We have an email address I should share to AEF requests. I'll put it in the AEF request external, put it in the presentation, but you can email us directly if you don't want to share on the bug. But in any case, best way to let us know what you're interested in.
Okay, so next question from Marceline. Two quick questions. One, is there a threshold for the training data to be used for the supervised classification? And the second one, how easy or practical is it to use embeddings on other software like JupyterLab?
So in terms of a threshold, if I'm assuming that means in terms of like number of points, we can start with as few as one. That's the similarity search. We just have 1 point and we can start to look for similarity. Usually we think in the hundreds to thousands, though. If you're looking at kind of a large scale map, you really want to make sure, more importantly than a sheer number of points, that you are representing the processes of interest. And so the embeddings know nothing about exactly what you want out of them. You can imagine, we've seen examples of, say, classifying utility scale solar, and we start to pick up on artificial turf, other things that are, flat and patchy and don't have a vegetation signal. So there's a lot more focus on good representative examples and good examples of what aren't the things you're interested in, making sure that you're actually partitioning that full label space, the embedding space, with the amount of detail you want. So I guess long way to say, the more detailed your classification and the harder the legend is, the more points you'll need, and the more you'll need to target those points to resolve uncertainties in the classification. For a very straightforward, kind of obvious classification, things like water, you might need just a handful of points to get a decent result. So it depends, but it should number in the hundreds to thousands, not like hundreds of thousands to millions. And in terms of using the embeddings on other software, yes, absolutely. So Earth Engine also has a Python API. All of the things I showed were in our JavaScript API, just to make it easy and in the web browser, but you could run using Earth Engine functions just like I did in a Colab notebook. And if you really need to work locally, you have the option to download those embeddings from us or one of the other providers hosting the embedding data set, and do anything you would do with normal downloaded images, just using the embeddings. So is it easy and practical? It's a little bit more startup cost. You have to know how to manage the images. You're going to have to manage your downloads. You have less storage available, but it's certainly easier than having to download and process huge amounts of raw imagery from source.
And on the same topic, is there a maximum number of training data that I can use in Earth Engine? So there is a limit.
Yes, and if I'm remembering correctly, it's a trade-off between the number of columns in, like, it's actually in the like tables themselves. So like the number of features versus the number of rows. And I don't have the kind of back of envelope for that. I do believe it's documented in some of our developer tutorials. So I'd encourage you to look there in more of the generic classification background, since it's the same workflows. But yes, there are limits to how many rows versus how many features. Embedding Stardust with 64 features, which is low in the sense of deep learning models, which can be, other embeddings maybe twice the size, many times the size, but still, you got a large number of features to start. You can then have kind of fewer of the training points, but it's still a pretty big number, if I'm remembering correctly.
Yeah, there are thousands, 5,000 if I'm not wrong, something like that. Anyway.
Yeah, that sounds
This
reasonable.
is the order of magnitude in any case. Yeah. And then Rohini?
Yes, I know we are a bit over time, but hopefully if it works for you, we could extend a few more minutes to be able to go through some interesting questions coming through. I have a specific one from Vitaly here. The description of embeddings data product on source cooperative states that 2017 embeddings have a data quality issue, which is being addressed. Could you please share the detailed description of this issue if it exists publicly somewhere?
Yes. So we have actually updated the Earth Engine copy of the data set. We reprocessed 2017. It was an issue with dropping Sentinel-1 images. We had a metadata issue. We weren't using the full number of Sentinel-1 images. Now, as I mentioned, embeddings are robust, our AlphaEarth Foundation embeddings are robust to sensor dropout. So we hadn't seen a huge effect in the embeddings themselves, but we realized we were missing some imagery. So we did go back. We wanted to hold to the claim we're using all that's available. And so we reprocessed. We tested. There was minimum change in the actual embedding values. If you were working with the 2017 data before, it shouldn't be a major issue, though we do say if you're reprocessing, go ahead. The latest version is in there. They were replaced in place. So what's in Earth Engine is the most up-to-date definitive source of truth and the best quality that we can stand by.
Okay, next one very quickly because still we have some questions. There is a lot of interest. So Luca saying, what is the added value of using embedded inputs on final land cover results? Have you done any validation and comparison with other land cover products? And then he's saying, thank you for the interesting presentation.
Thank you all for attending. Yeah, so the biggest added value, I would say, is lowering that barrier to entry. You can achieve, I mean, you can achieve probably comparable results, in some cases even better results if you go and you hand tune your features. You train your own model that's specialized for the task you're interested in. You pull out, specific indices, but that is all at the cost of knowing how to do that in the first place and spending all that time and compute. Embeddings are our best representation across all of these different data sets. We have run the compute for you. We've optimized for things like making them compact so that you weren't dealing with these huge feature vectors. We've done all of that structuring of the embedding space so they should just work out of the box. There's not artifacts. There's not gaps in coverage. So you get consistency, you get compactness, you get all of the different data sources, and you can move a lot faster. Now, that said, you can start to hybridize. There's nothing stopping you from attacking on other values to the feature vector, combining however you want with other data sets. But really, our goal was to make sure that folks who want to start with their label data and make maps could do that as quickly as possible with as little remote sensing expertise. You still need to understand your training data and a little bit on the classification side, but it was more about lowering that barrier of entry. We've compared with other data sets just in kind of more qualitative. So we've got some other examples I didn't show today, sampling and comparing with like CDL data sets. We've sampled other land cover maps, but really we're looking to the user community to compare what have you been currently doing? How does it get better? How does it change when you use the embeddings instead? And since the embeddings are structured just like regular images, you should be able to just plug them in anywhere you were using 10-meter data and do those comparisons and let us know. We want to see the papers, we want to see the blog posts, and we want to hear in forums like this how that sort of comparison work is going for folks.
Oh, thanks, Mari. That's quite impressive. Here's one last question from Anton for making your own dataset, categorical supervised classification. The GLANCE dataset is straightforward, but he was wondering if you could give an example of a bad set of labels that might not be well represented by the embeddings.
I hesitate to call anything bad, like one person's data is another person's noise. Embeddings, I would say, is an easy answer, are designed to represent surface properties. So atmospheric is perhaps more challenging. That said, we've seen air quality, but that correlates very strongly to the land features. And so keep in mind, if you're looking for things that aren't necessarily surface properties, that is what we're trying to represent. If it's kind of that one hopped removed, you've got to keep that in mind. and what those are more correlation rather than kind of direct labeling. We're not measuring the PM 2.5 of the air column. We're measuring the correlation to, say, on-road activity. We also, with the annual embeddings, it's hard to do sub-annual changes. We've seen a lot of struggles, especially in crop type mapping. If you're dealing with multiple crop cycles, multiple crops per year, you have to think about your labels with the annual embeddings as an annual period. So you wouldn't have a label that's necessarily corn. It might be something like corn, soy, I'm going to botch my crop sequencing, but crop 1, crop 2, crop 3, that represents the crop sequence over the entire year. And you'd want even a different label. It might be like a 12-part label where you have each month labeled by its crop. So you're getting very complex if you're trying to represent multiple types over that longer period. So the better the labels are aligned with an annual representation, the better suited they are to the satellite embedding data set. And then going back to the point earlier, if you've got those sub-annual use cases, if you've got labels that are not working with annual embeddings, we'd love to hear what those use cases are, and we can start to think about where that'll fit with kind of the sub-annual and like full model capability generation.
Yeah, and I have a last question is by me, this one. So I was wondering, as when we have many bands of the satellite imagery, we can apply like principal component to see which are the most relevant component. Can we think to embeddings again as bands where the spectrum is not the spectrum of radiation, but is the spectrum of attention? If we want to, I know it's an abstract concept. It doesn't exist, this concept, but in your opinion, is it possible to consider some principal component applied also to the embeddings to extract at least the most important component or reducing the number?
So it's a complex answer. I would start by saying the embeddings effectively are a learned transformation of the bands. Now, unlike principal components, there's no ranking associated with them, but they are a reduction and transformation such that we've already reduced into these 64 axes. But again, they don't have necessarily an ordering to them. You can run principal components on the embeddings. We've seen it done. Now, the thing to keep in mind there is if you were to run principal components over the locations from our training set, that piece of the modeling setup where we're actually trying to make sure the embeddings are pointed in all different directions, we're using that full sphere, you should start to see that everything should be relatively uncorrelated, at least where the model was trained. Now, in practice, if you run it on a small chip, you can get some very interesting axes. And some of our very early visuals, we actually did run PCA on like per image tiles, and it started to at least help you see kind of key features. But again, they're already designed to be uncorrelated axes. So you're getting effectively a PCA without the ranking or importance piece. And so would encourage folks to use them in their entirety. They're already a huge dimensionality reduction, and they're designed, again, it's the full set of 64 numbers, as opposed to trying to pull out any single channel or reduce that even further, since it's quite a reduction in the first place.
Okay, thank you. Thank you so much. It was a super interesting webinar workshop, and thank you so much to all of you. I will give back the floor to Rohini because we must close. Thank you.
Thanks, Maria. Thank you very much, Valerie and Cataline. This is a great webinar, and we're sure geospatial technology has definitely entered a new era here, and these solutions will really fundamentally change how we see and understand the whole world around us. And I can't be more excited. So really a big thank you to both of you. And as always, a big thank you to Maria for having moderated this event, and to all of our participants for being here. We're sure you were able to learn something new today in this workshop. All the materials will be available in the neural network. And of course, also you can watch the recording on YouTube and the neural network at any time. I just want to quickly remind you all the next planned event for the GeoAI Discovery on 22nd January, just next week. We will have a webinar on Introduction to Tessera, time series embeddings for geospatial analysis, followed by hands-on on Tessera on the 2nd of February. We also have 2 other workshops in the pipeline by NASA and IBM on geospatial foundation model. On 25th February, we will have embeddings workflows for Earth observation tasks. And on 19th March, it will be an introduction to TerraTorch. So many exciting developments. Stay tuned. And thank you all again for your participation. And with this, let me give back the floor to Anna.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for good.